All right, kiddos, here goes notes part 2 for week 14, where we're still talking about exponential functions, but more specifically about the base e. So the base e comes into play in nature frequently. The number e, it's a transcendental number, so it's approximately equal to 2.71828, etc., etc. So it's a non-terminating, non-repeating decimal like pi. It's very useful to us, and when you go on in math, so in calculus, you'll get to this, where if we graph y equals e to the x, the slope here ends up being 1. So well, I'll just leave it at that. So it ends up being very helpful to us in calculus when we're looking at the slope of the function. But the reality is that if we are dealing with bacteria or radioactivity or whatever, we can use that as the base, and it ends up being helpful. So we'll work through one example where we're talking about interest that is compounded continuously. And so continuously is kind of the limit of being compounded frequently. So we could have interest that's compounded every year or every month or every week or day or second until we have these smaller and smaller time intervals where it's actually compounded continuously. So every little small fraction of time, you would be earning some small fraction of your percent interest. So it goes like this. Our equation looks really similar. This is e, the transcendental number, and so this kind of replaces that term, the 1 plus r over n. The variables remain the same. P is the principal, or the original amount. R is the interest rate in decimal form. And T is the number of years, because normally when we talk about something like 6%, that's 6% per year. Okay, so here's an example. Yesterday, in notes part 1, we talked about Joey investing $1,000 and earning 6% interest for 3 years and for 30 years. So let's do that same question, only Joey's earning $1,000, or he invests $1,000. He earns 6% interest for 3 years, but it's compounded continuously. So if we substitute in, we end up with this. So we have original amount, we have E as the base, and there will be E. If you're using Desmos, you can just go to the alphabet and use the letter E, and it's being raised to, notice how 6% is in decimal form, okay? That's a common mistake. And then this is number of years, and we end up with, or Joey ends up with that many dollars, $1,197.22, which, if we compare it to, this is what we calculated yesterday, and that was compounded monthly. So notice how it's not significant, right? But he does earn a little bit more when the interest is compounded continuously. So the more frequently the interest is compounded, the more you earn. And so that is shorthand notation, but what I just said was the more frequently interest is compounded, the more you earn. All right, so let's look at 2 examples from the homework, and they go like this. So compound interest, again, we've talked about this, but here it goes. So if $2,500 is invested at an interest rate of 2.5% per year compounded daily, how many days per year? Find the value of the investment after the given number of years. So 2 years, 3 years, 6 years, here's our given information. 2.5%, this is what we would be using for our interest rate. That's in decimal form. Our value for time is going to be 2 or 3 or 6 years. N, the number of times the interest is compounded per year, is 365. And, you know, there's that whole leap year thing. Some people get super technical, and they're like, well, actually, the average year has 365.25 days, because, every 4 years we have a leap year, but we can use 365. That's good. And the principal or original amount is $2,500. So each of those setup looks like this. And I used Desmos to calculate these, and the cool thing about Desmos is I had all this typed in, and then I could just backspace and delete the 2 and call it a 3, and backspace, delete the 3, call it a 6, and I didn't have to retype all that stuff. So notice how the longer he has the investment compounding interest or earning interest, the more he earns, obviously. So you should try those and make sure you get those numbers. Okay, so bacteria culture contains 1,500 bacteria initially and doubles every hour. So when something doubles at the end of some time period, do you see how it's increased by 100%? All right, so if originally there were 4 bacteria, right, and it doubled, there would be 8 bacteria, so that was an increase of 100%. So what we're using is 2 for the base. It was, in my mind, I thought that would just be super clear when I explained it, but maybe it wasn't. But the fact that it doubles every hour means we can use 2 as the base. Here I can explain that slightly differently. So if we have 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, and 2 to the 0, so that's 1 and 2 and 4 and 8 and 16. Do you see how this is doubling each time the exponent increases by 1? So if this were number of hours, 0 hours, 1 hour, 2 hour, 3 hour, 4 hour, we can see that the amount is doubling every hour. Okay, so that should, hopefully that makes more sense. All right, so if it doubles every hour, we're going to use the base as 2, and the exponent t is measured in hours. So it's important to know what time value you're talking about. T in the exponent is not always years. All right, it depends on the information you're given. This is doubling every hour, so t is in hours. So we could say this is our formula where this is the amount of bacteria after t hours. P is the original amount of bacteria. 2 is the base because it's due to the fact that it's doubling, and t is the number of hours, not years. So substituting in, let us see, we have this as our equation, and part B, how many are left, or how many bacteria are there after 24 hours. So it's doubling 24 times, which ends up being quite a bit. So that's 2.5 times 10 to the 10th, which is many bacteria. You should ask me about the story of chess. And there's a good story associated with that and things doubling. All right, thanks for listening.